Good day everyone, my name is Prottay and today I'll be presenting our work on a mobile testbed for Synchrophasor technologies teaching and demonstration. This work was done in Alset Lab in Rensselaer Polytechnic Institute in collaboration with Dominion Energy. So we all know that the phasor measurement units or PMUs are changing the way we see the power systems. They are well suited for generating a lot of data by monitoring the systems in real time, and they are excellent for tracking real time dynamics. uh, they are excellent for tracking the situational awareness, and they are becoming the norm for power system monitoring and protection. But this addresses a question that do we have adequate infrastructures to train students or engineers for on PMU operations or on how to utilize synchrophasor facilities from industry grade equipments? And when we have them in industries, most of them are for trained personnels, and are there infrastructures that are safely operable for newcomers? So to address these issues, in this paper we have implemented and we are proposing and demonstrating a mobile test bed for synchrophasor testing and analysis. So the hardware architecture and the low voltage infrastructure and the softwares utilized, and the documentation of how to make the system work, everything is reported in this paper. And some of the prospective teaching and training modules are also proposed. Now we must remember that this rack, as shown in the right, contains a lot of industry grade equipments, beginning from the triangular, not triangular, I'll say it's conical shaped uh, mm, GPS antenna that sends data to the synchronized satellite clock cell 2488. Now, cell 2488 is a, a is capable of generating time signals. It's capable of extracting timing information from GPS signals, and the timing information is, uh, at least in our observation, a few microseconds level of accurate. Now we also have a power quality meter, cell 735. So it's an evaluation equipment which is able to record and log detailed information about various parameters in power quality, like supply voltage, frequency, flicker, deeps and swells, etc. Everything is compliant with C37118 standard. We have a protection PMU slash relay, which is cell 421. It is able to provide distance protection, under frequency protection, thermal overload protection, and it is also C37118 compliant, and it's a PMU. It can operate as a PMU. We have another phasor data concentrator which receives PMU data from multiple PMUs over a serial link or over an Ethernet link, and it can receive up to 240 messages per second from each device, so it's extremely fast. Additionally, on the bottom of the rack, we have a low voltage interface, which is a programmable National Instrument cRIO device, which can generate a 5 volt programmable voltage signal, 3 phase, and those voltage signals are connected to our PMUs through the AMS low voltage interface. This particular connection is made through a ribbon cable, as you can see in both of the pictures. Actually, in the picture on the bottom of the slide, the ribbon cable is the one that goes from the uh, second breakout board unit, and this actually goes inside the relay, as you can see in the picture on the right. Now, how does the entire thing works? So in this slide we are talking about both the software and the hardware. So we have already talked about that a clock exists in the system. So the cell 2488 clock receives GPS signal, and from that it extracts the timing value and it sends them to all the cell devices across the across our test bed. Now our Ethernet connects all these PMUs like cell devices like 735 and 421 to the PDC, the cell 3573 PDC. And now we also know that our compact cRIO, the NI device, provides 3-phase low voltage analog voltage signals to all the relays. So the relays or PMUs, they are reading PMU data and they are sending that PMU data to the PDC, and we are observing the PDC through a GUI over our computer. The same computer is being used to communicate with and program the compact cRIO, which had generated the 3-phase voltage signals. So the softwares utilized in this overall infrastructure was cell accelerator for all the cell devices, and for the compact cRIO, LabVIEW. Now this slide has a lot of information. We begin from the top left. Over here we are showing the GUI designed in LabVIEW that provides a current input to the relay, and we can see on right of that we have the IA, IB and IC at around 33 amperes, and they are perfectly balanced. The phase difference is 120 degrees. These are observed from the cell relay. On the extreme right of the slide we have the voltage input, and on left of that we can see that the voltages are around 22 kilovolts and the currents are 0. So both current and voltage measurements are possible. Now the overall infrastructure of this voltage and current generation in LabVIEW is shown in the bottom right, and you can see that we have the programs like the host side rack control. It just enables us to send data to send analog data via the model to the relays. And on bottom left we can see that the PDC has received data from the cell 421 and cell 735 relays, and we can see the number of received data frames in real time, and we can also see the voltages and currents over on the bottom left. So this is the overall software infrastructure of the work, and this is how it is possible to validate or debug using an external scope. We can measure the voltage or the voltages that's being generated by a compact cRIO from the breakout board directly to a scope, in case one of our PMUs or relays malfunctions. Now we also did one overcurrent testing. So to do this overcurrent testing, what was done was the phase overcurrent function feature was enabled. So the relay will react anytime the current applied to the relay is more than the threshold current set in the there. This can be set in the accelerator quick set for any of the 3 phases connected to the relay. When any of the 3 phases exceed the overcurrent limit, the 50p1, the tar 50p1 bit changes from 0 to 1. Now there are two ways to monitor them. The first is to locate that on the physical cell relay, but we don't always have access to the relay. So the best way to monitor them is by the uh, quick set terminal. As you can see, on the within the red box, we are showing that before and after applying the overcurrent settings. This by this switch, the on the 420 on the left view side, and we can see that the tar 50 p1 flag goes from 0 to 1. The right hand side is the lab view implementation, and the left hand side is quick set monitoring. Now in this slide we are proposing some of the prospective tutorials that we can manufacture or implement using our this infrastructure. So we can do balanced and unbalanced operation of the voltage sources or currents, because we can see them in real time via the PMUs and observe them on the PDC. We can see symmetrical components, as we have seen in the slides earlier, that the cell relays can be able to provide the sequence components in real time without any problem. We can do the protective relay functions, because the cell relays, especially the 421, are very capable of doing under frequency, overcurrent, uh, and under frequency, overcurrent, and over voltage protections. The next part of the tutorials will be a little more complicated. So we can do a PMU data transfer experiments on PMU data transfer and communications. So we have to introduce Wireshark to see the data coming out from the cell 421. We can see that the same data is being received as cell 3573 PDC. So this is another very good demonstrable tutorial for graduate students or industry people. We can do experiments on time synchronization, uh, which is possible because we can manipulate the IEEE time distribution, and the GPS timestamp is open and available for access. We can do PMU compliance because LabVIEW compact cRIO is very programmable. So applying step or applying a modulation signal will not be very mathematically difficult in that platform. And we can actually implement the real time simple PMU applications like phase angle measurements uh, using our testbed. But these experiments and these modules will be for more advanced users. So thank you, and you are free to ask if you have any more questions on this topic.